All right, so right now you should go ahead and have your notes out, either that you've printed or you should have paper out so you can take notes. You should have a calculator because you're going to need one. It's physics class. Come on, take care of business. What we first have is basic definitions. These were words that were on that vocabulary list that I gave you last unit that some of y'all were like, we didn't cover all the vocabulary words. That's because that was the vocabulary words for 3 units. Okay. A standing wave is a wave pattern that results when two waves of the same frequency, wavelength, and amplitude travel in opposite directions and interfere. So keywords for this would be, let's use my white, would be two waves. They're a resulting two waves. They travel opposite directions and interfere. Okay, a node is going to be a point that undergoes complete destructive interference. If it's destructive interference, does it mean its amplitude gets smaller or larger? It should mean that it gets smaller. Okay. Now, an antinode is a point halfway between two nodes, and the thing you need to realize is it has the largest amplitude. It has the largest amplitude. It's the point on a standing wave with the largest amplitude. If and when we get to do the Wiggler lab, you guys will see this really clearly, okay, as nodes and antinodes, and you'll be able to pinpoint it. I'll also do a demonstration with a mini Wiggler machine, and I'll show you them in just a minute. So everybody understood, looking at this, where our antinodes and nodes were. So for the first wave, how many antinodes? 1. So we had 1 antinode right there. Okay. And on the second wave, how many antinodes? 2. Okay. And for the third wave, 3. 1 for each spot. Now for the nodes, we said that these ends could count as nodes for the first one, so that they would have 2 for this first one. If we were counting the ends as well as nodes, what would we count on the second wave? 3. We could count 1, 2, 3. But I did primarily say this is really the only node because that's where the destructive interference occurs. Okay. And on this third wave, okay, we said there was 1 there and 1 there, so we could have said 2, or we could have said 4. Yes? Depending on what they ask you in a question. If they ask you for more nodes than antinodes, obviously they're counting the ends as well. If they ask you for fewer nodes than antinodes, then they're asking for only the middle ones. Does that make sense? Because I can tell you, you're probably going to draw one of these, okay, with a certain amount of nodes and antinodes, because I want to know that you know the definitions. All right, moving on, types of waves. There's a bow wave, and this is the V-shaped wave, produced by a moving object on a liquid surface. So this is V-shaped wave, moving liquid surface. So I would have done moving object, liquid surface. It's moving faster than the wave speed. So you guys see this when people are water skiing. You see bow waves. All right, a periodic wave. Remember, this is a form of periodic motion. This would be our simple harmonic motion or periodic waves. And then we had our transverse waves. Remember, transverse waves vibrate how? Perpendicular. You've already written those definitions. This one, and the next one, I believe. You've already written their definitions before in your notes. A longitudinal one is where they vibrate parallel. Remember, this is always to the direction that the wave's traveling. So really, the bow wave was the only new vocabulary word on that page, because all the rest of them are already in your notes somewhere for simple harmonic motion and waves. A lot of the information that we covered in the last unit will come up again in this unit. So don't get rid of those simple harmonic motion and wave notes, because you're going to need to read back over them before this next test. Because you'll notice this next test's title is Waves and Sound. So we are going to be doing sound and music, which we tie in together, and it'll continue to pull that wave information that I just covered in. Are we good? All right. Continuation on those types of waves. There's a shock wave and there's a sonic boom. These are both new vocabulary words for you. A shock wave is actually a cone-shaped wave. It is produced by a moving object that's going supersonic speed. It is moving through a fluid. That fluid, remember, is any particle that or anything that allows the particles to flow. Air is a fluid. Now, a sonic boom is a sharp crack heard when a shock wave sweeps behind an aircraft, and it's heard by a listener. So it's when that shock wave reaches our ears, we hear the crack from the shock wave. So those are two new vocabulary words that you guys have. So sound is a longitudinal wave. It's produced by a vibration that travels away from the source through solids, liquids, or gases, but not through a vacuum. Because it doesn't travel through a vacuum, you need to realize that it is a mechanical wave. So sound is a longitudinal mechanical wave because it does require a medium. Now, longitudinal means it travels how, James? Parallel. Recall that in longitudinal waves, compressions and refractions are produced by the vibrating motion. The compressions are regions of high air pressure, where the refractions are regions of low air pressure. You could take a sand, pull it through shovel, you could pull a shovel through sand, and as it hops, it would actually make big piles of sand, and then it would dig down, and then it'd make big pile of sand, and then it'd dig down. That's kind of an analogy of way to think about a compressional wave or a longitudinal wave. Since a sound wave consists of a repeating pattern through high pressure and low pressure regions moving through a medium, it is sometimes referred to as a pressure wave or a compressional wave. Now, the above diagram can be somewhat misleading if you're not careful. The representation of sound by a sine wave is merely an attempt to illustrate the sinusoidal nature of the pressure-time fluctuation. Do not conclude that a sound wave is a transverse wave. A sound wave is not a transverse wave. It is a longitudinal wave. It's important that you remember that. Sine waves are not sine waves. Sound waves are not transverse waves. They are longitudinal waves. So notice if we have the high wave velocity versus low wave velocity, we have a shorter wavelength versus a longer wavelength. You guys are okay with that? Yes? Okay, when a pressure wave reaches the ear, a series of high and low pressure regions impinges upon the eardrum. The arrival of the compression pushes the drum inwards, the eardrum inwards, and the arrival of the refraction serves to pull the eardrum outwards. The continuous arrival of low and high pressure regions sets the eardrum into vibrational motion. While you're in my class, your eardrum vibrates a whole lot, if you're listening to what I'm saying at all. All right? Because my sound waves automatically make your eardrum vibrate. That's what your eardrum is doing inside your ear right now, as you hear me. Okay? Kind of weird. We don't feel it. That's what it does. All right? Basic parts of the ear. You're not going to want to write all this down because there's a lot of information I give you here. You have the outer ear, and it's roughly to collect and channel. That's what you want to write. Outer ear, collect and channel. Middle ear. Okay? The middle ear transforms energy into vibrations. Transforms energy into vibrations. The middle ear is where your eardrum is, the three little bones, all of those that are going to vibrate against one another to reach your inner ear. You then have your inner ear that's going to transform the energy of a compressional wave into nerve impulses. Those nerve impulses go to your brain, and your brain then figures out what that sound actually is. A lot of y'all are prone to ear infections, or you have been in your lifetime. I know my little one is. And a lot of times what happens is this eustachian tube right here. When you're a little baby, and babies will have them typically more than adults will, when you're a baby, those eustachian tubes are flat, okay, almost horizontal. And as you get older, they drop down. As they drop down, that allows drainage to occur. But when babies typically can't sit up and things like that, and because they can't sit up, they're on their backs a lot. And then if the people feed them when they're on their backs, they allow the babies to hold the bottle themselves and drink while they're in bed, going to sleep, things like that. That liquid, if it sits in their mouth, will actually hang out in their ear. That ends up causing bacteria. That bacteria then ends up causing an ear infection. As you get older, again, lots of times your body will naturally be able to allow that to drain, especially when you get head colds. But sometimes it'll get so congested that it'll sit there and you feel like it's all in your head all the time. And that's why it's actually backing up into your ear. And as it backs up into your ear and sits there, that's when you end up with an ear infection lots of times. All right. Swimmer's ear is caused because water gets hung right here in your ear canal. So it's typically more of your outer ear that's going to cause an ear infection with swimmer's ear versus your inner ear, which is more of a bacterial infection. All right. The speed of sound is independent of pressure, frequency, and wavelength of the sound. So speed of sound is independent. However, the speed of sound in a gas is proportional to the temperature. So the following equation will be useful in determining the speed of sound in air. We will use this when we do lab of speed of sound. There's a speed of sound lab that we're going to do. And when we do that lab, you're going to have to find the temperature of the room, multiply it by 0.6, and then add it to 330 to figure out what the real speed of sound is in this room. So as the temperature increases, so does the speed of sound. So actually, when it's warmer, you can hear things further away. That's why jungles seem to echo so much, because the sound travels faster in a jungle than like in the polar caps. All right. 330 meters per second is the speed of sound at 0 degrees Celsius, and T is temperature in Celsius. So you have to make sure that you have your units correct. Are we all right? The speed of sound is different in different materials. Notice in air it is about 343, give or take. But in helium it's 965 meters per second. Notice through water that it moves at 1,482 meters per second. Granted, it moves 6,000 meters per second. Why do you think it moves faster through a solid than through air? Any ideas? So, because of the fact that a solid has the molecules really close together, the sound's going to travel through it faster because the molecules are already closer together. So they're going to bump more. Okay, it is 343 meters per second at 20 degrees Celsius. This right here is what is on your formula chart. The tax formula chart, it has that value for you given. We good? All right, applications of the speed of sound and its reflection and refraction. A lot of you guys know about sonar because if you have any type of boat that has fishing equipment on it that has a depth finder or any of that, then you're using sonar technology. Okay, depth finders, fish finders, range finders, all of those are going to use ultrasonic sound, and roughly that's for navigation. The depth finders are. Ranging, you can actually figure out how far something is away. Okay. I have a problem here that we're going to go ahead and solve. I got to figure out where I'm going to put this. There we go. 10 meters above the lake's surface, a sound pulse is generated. The echo, what is an echo? It's a sound, and it's what type of sound? A reflected sound. Okay, it's reflected. So the echo from the bottom of the lake returns to the point of origin 0.14 seconds later. The air and water temperatures are 20 degrees Celsius, and my degrees is missing. How deep is the lake? Okay, depth is a length measurement, yes? Okay, the issue here is the sound is above the lake water. It's generated above there, yes? 10 meters. So we already know that the speed of sound in air is different than the speed of sound in water, correct? So we're going to have to work this in parts because we have to find out how fast, because I know that it went down to the bottom and back up in a certain amount of time, correct? Because it said the echo. So if that's the case, I know that the speed of sound in air is 343 meters per second is what I'm going to say. The speed in water, though, is 1,482 meters per second. With that information, I could find out how long it was in the air. Because I could use the formula V equals D over T. You guys are going to want to make sure you pay attention to this question because you're going to have one like it on your assignments, which will all be due right after spring break. Okay, you're going to get them today, and they're all going to be due right after spring break. So I can find out that the time in the air would be 20. Because it's an echo, I had to go down 10 meters and back up 10 meters. Does everybody understand why I used 20? Okay. And I divided by the speed of sound in air, which is 343, and find out that it was actually in the air 0.058 seconds. All right. Then I want to find out how long it was in the water. Well, the total time that it went from the source back to the source was 0.14, and that was in my problem. I'm going to subtract from the air, the time it was in the air just now, and find out the time that it was in the water was 0.082 seconds. If I know time and I know speed, can I find distance? Yes, because I can use my V equals D over T. So you can do this part right here in the time it took to hit the bottom. I divided that by 2. Why did I divide it by 2? Because it went down and it went back up. You can do that at the beginning or at the end. This piece doesn't have to be done now. It could be done at the end. All right. So the depth would be distance is velocity times time. So 140, or excuse me, 1,482 times 0.041 would tell me that it's 60.8 meters deep. Now, if I had waited to do the divided by 2, I would have gotten that it was 121.6. And I would have had to divide that by 2 because that would have been the total distance it was in the water. And that would have been down and back. Does everybody understand why you could have done it before or after the divide by 2 part? Are we all okay with this? Because you're going to have to work problems like this. All right. Moving on. Rule of 5. This is just kind of more FYI, just so that you're aware. Some of y'all already know this. When you see lightning, if you'll start counting seconds until the sound is heard, the thunder, and divide that by 5, you can actually obtain how far the lightning was from you. Okay. So if you just count the number of seconds, a lot of people are just like, oh, count the number of seconds and that's how many miles away it is. It's roughly that, but really if you divide it by 5, that's more of a true rule of how far. It has to do with the speed of sound. It has to do with the speed of light and their proportion next to each other. Okay. The speed of sound is roughly 343. The speed of light is 300 million meters per second. So it ends up being a multiple of 5, actually. All right. Ultrasounds are something. These would be practical applications of sound that you guys are aware of. Ultrasonic sounds are used to image inside the body. They do a lot of other things besides just look at babies. But part of the reason they do ultrasounds for looking at babies is because sound waves don't hurt babies, where x-rays would. Okay, so this gives us a way to image inside of the body without damaging any cells. X-rays, by the way, you're not supposed to have too many a year. If you have too many, actually it can cause problems with some of your cells in your bodies. Okay, so just be aware of that. We detect 2 characteristics about sound, pitch and loudness. Pitch is how high or low sound seems. These would be new definition terms that you're going to need to write down because, again, this test will be largely vocabulary. Pitch is how you hear somebody's voice. Some people's voices are high and squeaky. They have those real high-pitched voices, and some people have those real low-pitched voices. All right, pitch is going to be how the frequency occurs. All right, I'm not going to show you this. We'll get to it. Pitch is measured by the frequency that the sound waves are made. The higher the frequency the sound waves are, the higher the pitch is going to be. The lower the frequency, the lower the pitch. When you play musical instruments, flutes, things like that are typically higher pitched, whereas basses and things like that are lower pitches. Okay, so then it has to do with the frequency. Loudness refers to the intensity of the sound. All of us are very aware of the fact that I'm loud. All right. And that's because my sound waves are very intense. Believe it or not, it has to do with the amplitude of my sound waves. And when I was a kid, I sucked my thumb for a really, really long time. Okay. I was almost 8 before I stopped sucking my thumb at night. But the roof of my mouth in the process, I didn't push my teeth out. I pushed the roof of my mouth up, okay, with my thumb. So literally like my thumb fits in the top of my mouth now because of how my thumb was actually shaped. I laid it flat. Okay, because of that, when I make sound waves, automatically they have a higher amplitude than most people because the roof of my mouth is taller. So the shape of your mouth alone affects how loud you are. Okay, so realize that right there is that is one of the reasons I know I can still talk quiet and I sound loud to me. And that just has to do with the amplitude of the sound waves that come out of my mouth. Okay, it is measured in the units of decibels. What is frequency measured in? What units is it? Hertz. All right. We all good with this? Or do I need to wait? What we hear depends on the frequency and the intensity of the sound. We hear frequencies in the range of 20 hertz to 20,000 hertz. That's what most of y'all hear. Mine seems to be a little wider than that. Um, this is called the audible sound range. Okay, when we talk about 20 hertz to 20,000 hertz, that's audible or sonic. Now, ultrasonic is anything above 20,000 hertz. You don't hear the ultrasound machine, okay, because those sounds are higher than our audible level. All right. And infrasonic is below 20 hertz. We don't hear that typically either. That's sometimes where dog whistles, things like that will come into play. They don't fit in our audible range. Now realize because of earbuds, some of you have decreased your range automatically because that puts such intense sound into your ear all at once without any collection of that sound. A lot of y'all have lowered your sound range already in your lifetime. Um, you need to realize that your eardrum is a piece of cartilage, and that piece actually ends up getting tired after it vibrates. Have any of y'all seen drums before that have been beat on so much that they aren't tight anymore, or they have to be retightened? That's kind of the same thing with your eardrum. At some point, your eardrum doesn't work as well, and that's why older people are always like, "Huh? What'd you say? I can't hear you." My father-in-law, we go to his house, and he has to have the TV blaring all the time. We're like, "Oh my gosh!" And part of it's just because he cannot hear it. And as you get older, that eardrum doesn't vibrate as well. It doesn't make those bones work as well, and therefore the hearing isn't as good. Now, there's other reasons why people lose their hearing, but that is one of them. So just be aware of that. An oscilloscope can be used roughly to see and measure sound waves. You don't really need to know a whole lot about it, but the oscilloscope just displays period from which frequency can be calculated. The amplitude or loudness is the energy carried. So relative intensity, what we hear is also affected by the motion of the sound, but normal breathing is at about 10 decibels. Okay, whispers are at 20, conversations are at 60, street traffic is at 70 decibels, rock concerts are 115. The threshold of pain that is going to hurt your ear is somewhere around 120 decibels, and the jet engine is 140. You don't see anybody that loads luggage onto airplanes just hanging out down there on the runways. They always have those big earphones on, and that's because they don't want them to have hearing damage just because of their job. And it hurts their ears when they have to hear all that plane engine noise. Okay. Realize if you stand closer to the speakers at a rock concert, obviously that's going to be decibels that are higher. Okay. The movie to the left shows a stationary sound source. The sound waves are produced at a constant frequency, and the wave fronts move symmetrically away from the source at a constant speed of v. The observers at A and B hear and that should say HEAR, not that here. So let's fix that. Hear the same pitched sound because the sound waves are coming at them the exact same way. Does everybody see this? Because this leads us into the next formula, which is big into this unit. In the movie below, though, the same sound source is now radiating sound waves at a constant frequency in the same medium. However, the sound source is moving to the right with a speed of 100 meters per second. Which one do you think is going to hear a higher pitch? A or B? Why do you think B? Okay, they are more intense, but they're going to hit B with a higher frequency. There's less space between them. Okay, so that means that it will actually be listener A is receiving waves that are further apart, so they're going to hear a lower frequency, where listener B has them closer together, so they're going to have a higher frequency. This is like when you're driving and you're sitting and an ambulance or a fire truck comes up behind you, and as it comes up towards you, it gets higher and higher frequency. It seems to be higher pitched, and then as it goes away from you, it gets lower and lower pitched. That's because of this effect. And this is actually known as the Doppler effect. All right. This is when the source of sound or a listener are moving. So the pitch of the sound changes. The source of the sound and or the listener are moving. So the pitch of the sound changes. Smaller wavelengths, higher frequency, higher pitch. So this one would be a higher pitch, and this would be a lower pitch. We all all right with this? Now, light waves also exhibit the Doppler effect. This is where this redshift, if they're receding away from us, they're shifted towards longer wavelengths. So we call this a redshift. Whereas redshift measurements, actually astrophysicists have measured this, and believe it or not, almost all stars and galaxies exhibit a redshift, which that's why most scientists believe that the universe is expanding versus like closing in. Okay. Again, it's more that you just understand that red shifts mean that the light is moving away from us. It has a longer wavelength. Now, the Doppler effect. The pitch heard by the listener is given by the following equation. This is your new equation for this unit. We have F prime equals F sub S, V plus VO over V minus VS. A lot of letters and a lot of the same information. F prime is the frequency of the listener. Who's hearing the sound? That's the frequency that they're of the listener. F sub S is the frequency of the source. Okay, so we have the listener, we have the source. V is the speed of sound in air. And for most all of our problems, we're going to use 340 meters per second, unless it's actually given in the problem. But on your worksheets and on your problems that you're going to be doing, you're going to use 340 for that. So you might want to write that somewhere in your notes, 340 meters per second for homework, unless given. Now, Vs is going to be the velocity of the source. So how fast is the object moving, like the ambulance or the fire truck? Now, if it's a lighthouse or a lighthouse that's making like a foghorn, obviously, is that moving? No. So what would the velocity of the source be? 0. Then your V sub naught, okay, or VO, is going to be your velocity of your observer. Now, I will tell you, some people are going to want to use F instead of F prime. They're going to want to use FO because that'll help them better with the observer thing. If you guys want to do that, I'm okay with it, but you just need to realize what you're choosing to use. Now, sign convention, you need to be aware of this. If the velocity is approaching us, or if we're approaching it, we're going to use positives. If we're going away, we're going to use negatives. So if the object is moving away from us, it's going to be a negative velocity. It's coming towards us, it's going to be a positive velocity. Are we all right with that? I'm going to do, I think, 1 or 2 examples of this with you, and then I'm going to set you free to work on your homework assignments. I'm going to hold off on the lab because I'm not here. Yes? All right. A fire truck siren. If you haven't been paying attention, you need to start paying attention now. A fire truck siren emits sound at a frequency of 400 hertz on a day when the speed is 340 meters per second. What is the pitch of the sound heard when the truck is moving towards a stationary observer at a speed of 20 meters per second. All right, so we have to start off with identifying variables. We know our velocity or our speed in air is 340. Those of you that have it printed out, if you turn it to the back of your page and work this problem, it helps you a whole lot more than just looking at the problem worked out on the page. Your F of S, or the frequency of the source, is 400 hertz. Because what is our source? The fire truck. And what is the observer? A person. And which one's moving? The fire truck, because the person's stationary. Yes? Okay. So the velocity of the source is a positive 20 because it's moving towards us. Yes? And the velocity of the observer is 0. So now it's plugging into the equation. I will tell you, you need to put the fraction part of this equation in parentheses. It needs to be done first because you need to do all that information, then divide. Then you need to multiply. This is when we all get our calculators out and we make sure that we can actually solve the problem using our calculators. Because inevitably we get to the test and then we don't know how to use the calculators properly. So we have our 340 plus 0 over 340 minus 20 because this was a negative sign here, not because it was going away from us, times our 400. You should get an answer if you've done this correctly of 425 hertz, but make sure you can do this calculation on your calculator. Okay. Now, what would be the pitch heard of the truck if it was moving away from us? What would change if we're going to cause it to drive away from us instead? We'd cause the velocity of the source sign to change. So instead of it being a positive 20, it's going to be a negative 20. All right. So we have a negative 20 of our source. We're going to do the same equation, but now this is a plus sign on the bottom instead of a minus sign because a negative and a minus make a positive. So you should come up with 377.78 hertz, which is a lower frequency because it's moving away. When you guys get stopped by the train, you notice this because as the whistle blows and it comes towards you, it gets higher frequency, so it's higher pitched. And then as it goes away from you, it gets lower pitched. So it doesn't sound as loud anymore or screechy. Yes? No? Maybe? We're asleep, we don't care? Move on, Miss C. Okay. A stationary source of sound has a frequency of 800 hertz on a day when the speed of sound is 340 meters per second. What pitch is heard by a person who is moving from the source at 30 meters per second? All right. What's moving? The person or the observer, the listener. And what's happening with the source? It's stationary, which means it is sitting still. So its velocity is going to be 0. All right. So our variables would be as follows. We have our speed in air, which is 340 meters per second. We have our source velocity, or source frequency, excuse me, of 800 hertz. We have our, now why did I make this negative? Because it's moving from the source. So it's moving away. So we can plug it in. Now why don't I have anything else on the bottom? Because it's minus 0. Okay. Shock waves and sonic booms. We've already talked about these, yes? Okay, so I'm not going to say a whole lot about them, but that's really what happens is it creates a wave that starts overlapping, so you get constructive interference. When someone hears that, that's when they hear the crack. Okay? And that's what it looks like when it gets photographed, by the way, is when that wave actually is being produced. Okay? So the sonic boom is produced when the plane actually crosses the shock wave. All right, and that's when you'll hear it. So we are going to now work. There's a stack of problems by the turn-in box. There are different pieces of paper you need to pick up. There are PSE, practice and additional problems, and there's a waves worksheet. You are to start working on those. You can do problems 1 through 5 with what we've already done of the practice problems. You can also do problems 1 through 6 of the additional problems. And you might be able to work some on the waves worksheet. You need to do these as 3 separate assignments. Okay? Work on your practice problems on one page. On a different page, do your additional problems, and then work on your waves worksheet.